SOLIDWORKS Flow Simulation has several additional modules, each which add even more capability to our already powerful CFD package. All of these modules are embedded inside the existing SOLIDWORKS Flow Simulation interface, keeping the software dynamic and easy to use. Here we're going to look at the Heating, Ventilation and Air Conditioning module, or HVAC for short. Typically, the environment studied in this module would be anywhere people or sensitive equipment were present, or perhaps where radiation is going to be a major factor. So anything from a kitchen, where humidity and condensation may be an issue, to a data center to size the appropriate fans and ensure the servers are adequately cooled and evenly cooled. Or perhaps a large glass structure where not considering radiation is going to cause a major issue. In this first example, we're going to look at a section of an aeroplane. This is to ensure there is enough circulation of clean air and any contaminants are removed, while maintaining a comfortable and appropriate temperature. Firstly, we set up our flow simulation as normal, using the familiar boundary conditions and heat sources. Here we can see all the people have a temperature applied, and the inlets can be seen at the top of the model and the outlets at the base. Once this is complete, we can then run the study. We can then use the industry standard ISO 7730 comfort parameters to see what percentage of people will be unhappy with the draft from the air conditioning system. Since the HVAC module is embedded, we can use all the familiar flow simulation tools, such as this cut plot, which shows us any areas in red where the velocity may be slightly too high or the draft may be slightly too strong. So this percentage of people will be unhappy with that particular draft. Next, we can see what percentage of people will be happy with the overall temperature. We can do this by looking at the predicted mean vote, or PMV for short. This result parameter is based on social studies and considers the average thermal sensation of a group of people. The target here is to get to 0, that is the neutral aim and the ideal scenario. However, 3 would be uncomfortably hot, and -3 would be too cold or drafty. As with all SOLIDWORKS Flow Simulation results, we can quickly and easily change the plot. We can change the scale of the legend to help us better understand the results, and then we can quickly investigate further using the probe tool. From this, we can quickly and easily see the gentleman at the back is probably going to be too cold, so we can look to adjust the air conditioning system accordingly. But beyond this, we could also look at the quality of the air and see how long it has been in the system for. We can do this by using the local mean age plot, or LMA for short. Here we can see that extra ventilation might be needed in this area to help remove the stagnant air from the system. Another way for us to check the effectiveness of our system would be to look at the CRE, or Contaminant Removal Effectiveness parameters. These parameters are an index that provide information on the effectiveness of a ventilation system on removing contaminated air from the entire space. For a perfect mixing system, a value of 1 is very good. Anything below 1 is classed as poor. But we could take this a step further. For example, what would happen if one of these passengers sneezed? Ideally, we would like the contaminant to be forced down away from the other passengers, straight into the outlets and into the filters. But to see if this happens in practice, we can run a tracer study where a set amount of contaminant or admixture is placed into the existing flow stream. We can then see which areas would be affected by this. Here we can use this cut plot to see where this would travel. In this example, it's safe to say I wouldn't like to be sat behind this gentleman. But beyond this, we can study multiple tracers in one study, so we can clone the tracer and then release more contaminants into the air to see what would happen over the time period, and work out how we can best modify our air conditioning system to suit. But as well as these comfort parameters, tracer studies and the advanced material library, one of the other main features of the HVAC module is the advanced radiation method. Usually, SOLIDWORKS Flow Simulation uses a discrete transfer method, which is great for most studies, electronics cooling or turbulent flow problems. However, in this case, we have a large glass structure, which will be exposed to solar radiation. This method is much more capable and means we can consider geometric optical effects, such as shadows. The method we are using here is called discrete ordinates. This is required when studying semi-transparent materials such as glass because it allows for absorption, so certain wavelengths will be allowed to pass through and other wavelengths will be absorbed by the material. The HVAC module comes with a comprehensive building materials library, with this information already added in. On top of this, we already had a predefined list of locations around the world, complete with solar information. This library also includes an enhanced fan database to help you quickly and accurately specify the boundary conditions with real manufacturer's data. However, if the radiation in your study isn't solar, the HVAC module has other tools which will allow you to apply radiation to a particular surface or volume. We can do this either as a diffusive or directional source by selecting either power, intensity, or temperature as an input. All of these tools help users gain great insight into their designs, sometimes even more so than a physical test. For more information on this module or anything else, please don't hesitate to get in touch.